In 1996, Toshiba launched the Libretto line of sub-notebooks, and they're trash.
What did you say?
Well, okay, more accurately, they're often found in the trash or e-waste, and at a far greater rate than any other vintage laptop or computer at the time. This is for two main reasons, both we aim to solve in this video. First, the plastics. As we'll see, the choice of plastics used in these notebooks makes them incredibly brittle as they age. Now I hear what you're saying, all plastics degrade over time, and you're right, but plastics on the Libretto have become far more brittle far faster than any other vintage line I've experienced. Second, the BIOS lock. BIOS passwords were common in this and many other laptops back in the day, but in most other laptops you could simply remove a CMOS battery for a while or short a jumper on the system board while booting. Not this guy. It needs a custom hardware dongle that plugs into the parallel port. Two problems with that. While making a hardware dongle is not difficult for those that have the equipment and the skills, it's outside of the reach of most vintage collectors. The second is that if you do make one, you need a parallel port, a port in which the main unit of this laptop does not have. You need a dock, which are even more difficult to get your hands on than the laptop itself. These two factors contribute to this line of laptops getting tossed, recycled, or perpetually sold on marketplaces until they eventually crumble and make it into the trash anyway. So we're going to give this laptop a new lease on life by designing a new user-printable case, as well as creating a BIOS key that's cheap to make and requires no custom hardware to use. Without giving too much away, I want to thank Elegoo for sending over their brand new centauricarbon Core XY printer, and of course to our channel sponsor, PCBWay. More on both of them later, but for now, let's break this thing down. Well, literally. The first thing to do is test so we know if it works and what we might need to repair down the line. I'm using a variable output power supply, which saves me from storing a bunch of different supplies for different laptops. Essentially, all I have to do is find the right adapter after I dial in the voltage, and then I'm good to go. The good news is that it works. The bad news is there's this BIOS lock we're going to have to deal with later, but at least we know the laptop functions, so we'll start tearing it down. This is my first time tearing down a Libretto, so I don't know what to expect. There's a lot of things you learn when tearing down a laptop for the first time, like how many screws and sizes and components and how well it's designed. Also, no matter how careful you are, sometimes things break. And, well, unfortunately, this is going to be a common theme for this little laptop. And because we're planning on modeling this thing and giving it a new shell, then we're going to have to keep track of everything, even the broken pieces. My first impressions here are actually pretty good. You can tell that a lot of design considerations were taken into account, and what I mean by that is that it's clear that things were actually meant to be serviceable. These strain reliefs on the keyboard, for example, knew that this keyboard was going to be taken off and put back on, maybe by a technician or maybe by a user that simply wanted to upgrade the RAM. You tend to see these types of design considerations in higher-end laptops of the day, where simply removing a keyboard and replacing the RAM is relatively straightforward, but things get a lot more complex pretty quick after that. When this laptop arrived to me, it was in actually relatively good condition, but as you can see, things start to fall apart pretty quick, and this is not for lack of me being gentle. As we continue, we get to the CMOS battery. Now usually, pulling this out will disable any kind of BIOS password, but that is not the case for this model of laptop. As I've been going, I've started to notice that some pieces are breaking while other pieces aren't, and I'm starting to see why. The material designator between those two brackets means it's a magnesium alloy, specifically 9% aluminum and 1% zinc. It's super light and super tough stuff, which makes sense why the bottom isn't cracking. Even though I know I'm making a new case, I want to try to preserve things as much as possible. In order to remove this screw cover, I'm not actually cutting it with my scalpel. I'm using it to try to pry things up and let the solvent do the work. This is sped up quite a bit, and so this takes some time, but at the end of that, I'm not damaging or scratching the case, and I'm not damaging or scratching that screw cover just in case I want to use it or put it back again. As I'm going, I'm always paying attention on how things come apart so I know how they need to get put back together. The smaller and more intricate the electronic components, the harder it is in order to try to get things right and back into a really, really tight package. I'm also getting the first looks at the insides of the parts in order to see what I'm going to have to remodel, what I can change, what I can improve, and what I'm going to have to stick with. I always get nervous around ribbon cables. They are one component where if you have to repair or recreate them, it can be incredibly difficult if not impossible. And it's not necessarily the flat flex cables, it's the actual connectors on the end. Usually they were custom for this specific run of laptops and you're never going to be able to find them on a supplier website. After I'm done, it's time for a little inventory. I make sure to sort every screw and look at all the little plastic pieces to start figuring out how I'm going to model and print them. These projects are usually a months-long process for me, and so I need to make sure that I have everything organized. But with all that behind me, it's time for the fun part. The librettos weren't really known for having a bright screen, but I did want to make sure that I took the opportunity to go in, take a look, repair the backlight, and quite honestly, just see the thing. This is the first time I'd ever really torn into a libretto before, and so I was more curious than anything and wanted to make sure that while I was in there, I made the repairs that needed to be made. After I carefully remove this foil shielding, I can peel it back and start to see what's inside. Now, all LCDs are going to have some type of similar setup inside. You can see the column drivers on the top and the bottom and the LCD driver board on the right. The trick is figuring out how they're all put together and making sure that we can put them back in the same way. Unlike the initial parts of the laptop, these parts are not meant to be serviced at all. You can see that there's been some hot glue added for strain relief, and that cable right there is the cable to the backlight tube that we're looking for. And after a little bit of heat and a little bit of coaxing, we can get that cable free and move that column driver board away from the top. After taking care of a couple more screws on back and a couple on the front, we can remove it from the outer frame so that we can start looking at the inner frame. I gotta say, this thing is pretty complex when it comes to the number of components, the frames, and how it's all put in together. I literally use my own videos that I shoot in order to go back and look at them to make sure that I can put it together correctly the way that it was taken apart. But after a couple more screws and a little bit of coaxing, we can separate out the backlight and the diffusion layer. Out of all the components in old vintage laptops, CCFL tubes are probably the most used and still widely available today. All I have to do is measure the length and the radius, and I can order a brand new one, super easy and very inexpensive. Installing them, however, is a little bit of a different story. I cut the leads to match exactly, and I just put a little solder on my tip of my iron in order to remove it with just a touch on either side. You want to make sure that you're using high heat with as little time as possible to avoid damaging the ribbon cable or wire that connects it to the power. When you're installing the new tube, take the same care. Tin the leads, and just a touch on that wire should solder it back. Once you're comfortable that you've got a solid connection, you can push back those rubber stoppers on either end. This one was a little bit of origami, so make sure that you know how you took them off in order to know how they go back on. Working on something this small means that tolerances are going to be incredibly tight. If something isn't going back together as easily as you think it should, pause, step back, and reevaluate. Because of the numbers of layers and components we're talking about, issues compound. The backlight not being seated correctly could translate to pressure being put on the diffusion layer, which in turn could put pressure on the frame, which may mean that the LCD wouldn't fit in the case, or may make the case not fit together correctly. I also like to clean at every part in the process. This makes sure there's no grime or residue or anything that could create long-term problems. I'm sealing the back up with a large piece of Kapton tape. I'll be replacing the metal foil shielding before the project is over, but for now, replacing the original high voltage label means this LCD is good to go. When I dive into a new modeling project, the first thing I look for are primitives. What I mean by primitives are circles, rectangles, those things that give you the basic dimensions of the outside of the overall shape. Things are going to be a lot more complex than that, but they all start from primitives. After you identify those, you can start adding tapers or bevels or cutouts or more organic features to the part. Now this case is really complex, but it all starts out with rectangles and straight lines. Just by handling this, the case is continuing to deteriorate, and I'm starting to see a pattern. The bottom of the case is almost crumbling. None of the breaks are clean, and the material underneath feels almost powder-like. And even though the top of the case is thin and still breaking, it's holding up quite a bit better, and we soon find out why. The material label for the top shows a combination of ABS and polycarbonate with glass fiber reinforcement. The bottom, on the other hand, is just polycarbonate with glass fiber, no ABS. Without going deep into material science, the amount of polycarbonate in the plastics plays a huge role. Essentially, it's incredibly tough when you first create it, but it does not age well. Pure polycarbonate is more susceptible to UV radiation, to moisture, and is less chemically stable than a polymer alloy or blend with another material like ABS. In contrast, this is a bezel for a 1995 ThinkPad, and it's made out of pure ABS. In my experience and under the same conditions, ABS fares far better over time, including the back panel, which is made from carbon fiber reinforced plastics. Jumping back to the libretto, I've started to use high-resolution scans for the modeling process. In order to get good scans, the parts need to be flat, and in order to make a oddly shaped part flat, I've started to use this blue tack. I can easily adjust it by putting a little pressure on one side or the other to get a completely flat scan. It's soft enough to adjust easily, and it's not sticky enough to leave any kind of weird residues on the part. I don't use these scans for the outer dimensions. That's still old school by using a pair of calipers, but once I actually have all of the basic dimensions dialed in, that's when I'll go back to the scans and overlay them on top of the part. This is the backside of the display. I'm overlaying the scan directly on the face itself, and I'm using the two holes for the mouse buttons as a reference for alignment. Once I've got it locked in, it makes placing the screw holes and the alignment pegs a much easier job. As I'm working on this step, I've got the part in front of me and my calipers so I can check the alignment and the dimensions in reference to all of the other pieces within the part. And at some point, there's only so much you can do before you need to print your first reference piece. And for this project, for both speed and comparison, I'm using two separate printers. One is my Bamboo X1C, and the other one is the Elegoo centauricarbon. Now I'm doing this both so I can iterate faster, but also to check out the centauricarbon. This is Elegoo's $300 Core XY printer that they are putting up pretty much right against the X1C. Even some of my reference prints can take 6 to 8 hours, and so I wanted to know if a $300 printer could help me iterate faster. So I put it to the test, side by side. If you watch the channel, you'll know that I use my 3D printer mainly for making reproduction cases for vintage electronics. And so the two most important things to me in a 3D printer are dimensional accuracy when it comes to things like rapid prototyping, and finish when it comes to things like printing off an actual part that I plan on sanding and prepping and painting and putting decals on. As you can see, I went through quite a few revisions of each one of these parts in order to get the final ones. There were times when I really wanted to do a like-for-like comparison and print the exact same part on the Bamboo X1C and the centauricarbon. Other times I just wanted to use the efficiency of having two printers so I could work on one set of pieces and be printing another piece at the same time. So what exactly I'm looking for is, over a large span, say 150 to 200 millimeters, I'm looking to be able to correct tolerances within the realm of about 0.2 millimeters. Now, of course, this depends on the orientation the part is printed in. So some I've printed on the base like this, directly onto the build plate, and others I've printed vertically. Now, both scenarios, I can say that these parts have been pretty identical to that which I've been able to get on the Bamboo X1C. Now let's talk about surface finish and accuracy. This is where the X1C continues to outperform. Now, when I want to make a reproduction part, I'm not looking for the part to be perfect right out of the printer, but I do want to minimize post-processing times. So having to do a few less passes of sandable primer or not have to use putty is a big win for me. While I have gotten some great finishes with the centauricarbon, the word I would use would be inconsistent. You can always correct for issues like under or over extrusion in the printer settings, but you can't correct for inconsistency. Now, this isn't a huge problem for me. It may just mean that I need to do a few more passes of sanding and priming than I would if I would have gotten the part straight out of the X1C. Overall, I want to say I'm really happy with the centauricarbon as a no-frills workhorse of a printer. Now, the cost of this at launch is going to be around $300, so obviously you're not going to expect some frills like you have on the X1C. You won't find things like automatic flow calibration, or AI failure detection, or even an AMS yet. However, the Centauri does come with some more advanced features that you'll find on more advanced Core XY printers, things like automatic bed leveling, input shaping. It also has a camera for you to monitor your prints, and you can print directly to it from Wi-Fi without the need of a cloud account. Now, one of my favorite things about the Centauri is that it comes in an enclosed chamber and supports more high-temperature filaments that require a lot higher heat and consistent heat as well. So I am comfortable saying that this printer today is great value for the money. Is it going to replace my X1C? No, it's not, but I am more than happy to add this into my workflow. So I want to thank Elegoo again for sending this over for me to evaluate. And with that, let's get back to the libretto. Iterating on the design and getting the dimensions just right is probably the thing that takes the longest. Every time I do a new print, I try to be as thorough as possible in checking all of the dimensions. I check to see if the previous adjustments lined up, I check to make sure that those adjustments didn't affect any other areas that I overlooked, and I check to make sure that there weren't any new things that I missed. Some of these parts can get pretty intricate, so I spend a lot of time removing supports and cleaning things up. And just when I think that I've got things set, big things happen like, the keyboard doesn't fit. The whole thing is a balancing act. You don't want to put too much time into designing up front because you know things are going to change. You don't want to change too many things between prints because that can cause other issues. You're also trying to optimize the print and finding the best orientation to print in for consistency. And every time you change orientation, your tolerances change because you're printing with thermoplastics, and thermoplastics shrink in different dimensions when printed. It's an iterative process of small 0.5 millimeter tweaks here and there until finally, you've got something you can use. Now normally, my final print would be the pristine print, the one that I'm going to go sand and finish and paint and apply decals to, but I'm going to go in a different direction this time. I'm going to have this professionally printed by our friends at PCBWay in a process called SLM, or selective layer melting. The material is going to be nylon 12 or PA12. The quality of the prints that come out of this process are incredibly tough, and after what this little libretto has been through, I think it deserves it. And while in the past I've recreated and applied my own logos onto the parts using a dry transfer process, PCBWay has the ability to print directly onto the piece using a silkscreen process, so that's what we're going to do this time. So while I would have usually spent a little bit more time trying to get the best finish on these pieces, I think they turned out really well. And before we send the final model off to production, we'll do one last test to make sure it all comes together. It always feels really good at this point. When you first start out a process like this, you don't know what you don't know. When you first start a teardown on a new laptop you've never worked on before, you start to understand how things are put together, but you don't really understand why. When you get into the modeling process, you start to question the decisions that were made. Some of those decisions you find out were purely due to the manufacturing process, the limitations of injection molding and the materials at the time. Other features aren't so obvious, and so you change them during the modeling process. And it's not until you start putting it together where you realize, oh shit, that's why they did it that way. I can't tell you how many times that I thought that I'd come up with a better way to do something in a model, or removed some material I thought was excess, or added some material I thought would be good for structural support, only to realize when I went to put it all together exactly why they did it that way. And don't get me wrong, part of my process is to go back and make these things more easily printable, and take advantage of the fact that we're not dealing with injection molding, we're dealing with FDM or resin printers. But when it comes to preservation, my entire goal is to make sure that these models are as true to the original as possible. Because we don't know what kind of manufacturing processes are going to be widely available in the future. As our little libretto takes shape, we can start to see one of the modifications that I made in order to accommodate the fact that we're printing this. This case used to have small plastic clips along the edges that I've replaced with these press-fit tabs. While they would have been easy to model, those clips would have been a nightmare when it comes to 3D printing. The rest of the case is held together by M2 screws, and I've used these heat-set threaded inserts in order to give them a really good connection. Those inserts will work on both this print and the nylon one that I'm getting from PCBWay. Everything is fitting together really nicely, so I'm going to finish up by putting back in the RAM, the keyboard, and finally the hard drive and the battery. Seeing how well this thing is coming together is getting me really excited for the nylon prints. But as we wait for those parts, there's still one more important thing to take care of. This pesky password. I've experienced a few different types of BIOS locks before, but I really wanted to take a look at the libretto and see for myself if there was another way in. In the 90s, there were a number of ways hardware manufacturers were able to reset a BIOS password. Typically, removing the CMOS battery would clear the password as it was stored in volatile memory. For laptops that were a bit more secure, the passwords were stored in a security chip. So, when removing the battery didn't work, I went on the hunt. I did identify one chip on the board that looked like it could be a security chip, but probing the pins and watching how it acted on boot ruled that one out quickly. So with no jumpers and no security chip to be found, the password is likely stored here, in a dedicated flash memory chip. And after doing a bit of research, it seemed like Toshiba had a custom hardware dongle that, when plugged into the parallel port, would reset the password. Now the good news is that I was able to find one page on how to create this dongle. The bad news? I didn't have a parallel port. See, the librettos didn't have a parallel port on the main unit, but instead relied on a dock. But if you don't have the dock, which a lot of people don't these days, what do? Improvise. If you look at the dock connector itself, it has all the pins that connect to all parts of the dock, including the parallel port. So the first thing I did was look up the pinout for the dock connector and then figure out which pins mapped to that parallel port. Next, I needed a way to connect to the dock connector. I looked everywhere for a 132-pin micro DIN or D-sub connector and came up with nothing. Even if I had, it would have been preventatively expensive. Plus, we're trying to make this doable for anyone. Then I had an idea. The gap inside is just over 1 millimeter, and the connector wires sit just proud of the walls, meaning I might be able to fit a 1 millimeter circuit board in there and get some good connectivity on either side, kind of like an edge connector or how a graphics card fits into a slot. It was worth a shot, so I got to work creating a custom PCB that had all of the proper wires and pins already connected together, so there wasn't anything else to do. When the first round came back, the 1 millimeter width was perfect and it felt like it was making really good contact on both sides. The length, that was off, as were the pin placements. You can see the pins don't align to the contacts on the PCB. So I tried another round. I sent it off to our friends at PCBWay, and then a week later, I had this. Now the only thing left to do was plug it in and try it out. Now before actually doing that, I wanted to take a look under the microscope. And while it's not perfect, you can see that the pins are making the connections on the right wires. So with all the work that I did, mapping the dot connector to the parallel connector and then wiring the pins together, if all that was a success, this laptop should just turn on with no password. And unfortunately, it still didn't work. Now luckily, I was able to find a friend that had a dock connector they let me borrow in order to do some troubleshooting. I was fairly confident the pins were making connections with the PCB, so the only other thing it could be is my wiring. There have been multiple instances when working on vintage computers, the online documentation or even the service manuals themselves are just wrong. So now the only thing to do was to go pin by pin and make sure that every pin on the parallel connector mapped to the one that I expected on the dock. And to my surprise, they were correct, which only means that somewhere in the mapping, I had made the mistake. Which, to be honest, is not that uncommon, it's just really frustrating at this point. I had found that I had wired 4 pairs of wires incorrectly in order to create the hardware key, but I wanted to be certain this was the only problem. I didn't want to do another round of PCB design and get those back only to find out that there was another issue. So I got out my microscope and soldering iron, got some incredibly thin enamel wire, cut some traces, and got to work. One of the things I had going for me is that there wasn't a lot of risk here. There are 5-volt pins coming out of that dot connector that could do some pretty serious damage if wired in the wrong way, but fortunately, those were pretty far away from the area I was working on. So after all that work, I plugged it in, powered on the computer, and I got this. Not only did the key bypass the BIOS, but it actually did it in a way that preserved the sleep state. This computer was coming out of hibernation from who knows how long. And just to confirm, I shut down the computer, took out the key, opened the BIOS, and the password was gone. It is bittersweet to end the video here, but it's honest. After working with the team to get the nylon case printed and accepting the risks, it just became clear that it's just not the right material and it's not the right process. While you can get really good, clean, detailed parts like this button set for the display, for example, the thickness and geometry of the case made this specific method not really viable. But for this video, I absolutely accomplished what I set out to do, which was to create a viable, printable model that can be made on a consumer-grade printer, thus preserving the ability for others to create reproduction cases and actually use these old computers without fear of them just crumbling in their hands. And so the model, along with creating the Liberty key to remove the BIOS passwords, will hopefully help keep these out of e-waste for a long time to come. I want to thank you so much for watching, and if you enjoy my videos, please like and comment and subscribe. You wouldn't believe how much it actually helps this channel to reach a wider audience. I also want to thank Elegoo for sending over their new centauricarbon, and of course to our channel sponsor PCBWay for their continued support. Now, if you don't mind, I'm going to get some doom going on this thing.